Hello everyone, my name is Shengyin Wang. Today I'm going to present our work on goal-conditioned model simplification for deformable object manipulation. This is a joint work with Matteo Leonetti and Memo Dog at the University of Leeds and King's College London. Deformable objects are everywhere in our daily life and have a wide range of applications from housekeeping, medical operation to industrial production. Compared to rigid objects, deformable objects pose two main challenges: high-dimensional configuration space and complex dynamics, which make both planning and learning time-consuming. To simplify the deformable manipulation problem, we have conducted some research trying to fill several existing gaps. Instead of defining key features manually, such as corners and contours, we want to establish an automatic feature extraction method that is adaptive to different goals. Instead of using the expensive fine models, we want to find a simpler model with acceptable accuracy. Instead of learning high-dimensional space, we want to find a compact state representation that captures the most important and relevant information to achieve the task. This leads to the work we are doing now, namely as goal-conditional model simplification for deformable object manipulation. Potential usage of the method includes simplifying the action space or state space for both motion planning and policy learning. In this work, we focused on action space simplification for manipulating ropes and clothes using cross-entropy method as a planning algorithm. Given the goal configuration, our model simplification method will find the minimum elements to approximate the original model with acceptable accuracy. Depending on the types of the deformable object, line fitting or mesh simplification will be called. After model simplification, a set of key points will be extracted as graspable points, which can reduce the searching space for CEM-based motion planning. For line fitting, we start from using two key points to approximate the original model. The position of the key points can be anywhere in the space. We use quadratic programming to find the optimal position based on our defined distance error metric. If the approximation error is below the threshold, the simplified points and line segments will be outputted. Otherwise, we will gradually increase the number of key points until the precision is satisfying. As in the example shown above, 4 or 5 points give a much simplified model with minor errors. The same idea applies to close approximation, with the only difference of using off-the-shelf mesh simplification toolkits from MeshLab. For a piece of clothes folded sideways, a simplified mesh with 6 triangles has a small enough error to approximate the original model. After model simplification, we use the simplified model to reduce our defined action space by extracting a small number of key points on the original model as graspable points instead of searching in the action space of all points. The bottom left figure shows the extracted key points in blue pentagons, while the bottom right shows the motion plan based on the simplified action space. Finally, to demonstrate the effectiveness of our proposed method, we conducted a set of comparative experiments on 4 tasks. Due to limited space, only the results of close diagonal folding are shown. As we can see from the same initial state, CEM simple, which is based on the simplified action space, can successfully achieve the task, while CEM original cannot find a feasible plan with the same number of simulation steps. Additional results can be found in the paper. Thanks for watching.